This chapter is chapter 20, electric circuits. In this screenshot, there's a woman holding what I thought to be a stopwatch, but then I compared the size of the stopwatch with the size of her head and realized that that's not a stopwatch. If it is, it's the world's largest stopwatch. The point of this video is that stuff runs on batteries. That's actually a CD player. A battery creates an electric field which forces charges to move, which powers electrical devices. Checkpoint question 1. Have you ever seen with your own eyes a portable CD player? I'm not talking about something that you've seen on YouTube, but in person, live and in person, exciting device. Those portable CD players, but you don't see them very often, somewhat rare. We talk about electromotive force and current. Within a battery, a chemical reaction occurs that transfers electrons. So if you have an electrochemical cell like we did with our orange in our classroom, we can move electrons, which causes a current. Batteries are electrochemical cells, and they create what's called an electromotive force, or an EMF. EMF is measured in voltage. With electric current, we basically have a rate equation. The average drift of electrons through a conductor is measured in velocity. We're talking about the amount of charge moving through a cross-sectional area, perpendicular cross-sectional area per unit time. 1 coulomb per second, meaning coulombs on the top, seconds on the bottom, is the same as an amp. I stands for current and is measured in amps. If the charges move in one direction, we have a direct current. If they go back and forth because of the action of the generator, we call that alternating current. You could think of it like water in a washing machine with an agitator sloshing back and forth. That would give you alternating current, while direct current would be like water running through a garden hose, one directional or direct current. For example, the current in a 3-volt battery of a pocket calculator is 0.17 milliamps. In 1 hour of operation, how much charge flows in the circuit and how much energy does the battery deliver to the calculator circuit? In order to solve that, we need to know the equation I equals Q over delta T. In this case, we're solving for delta Q, or charge, so we would multiply the current times the time in 1 hour. In order to calculate energy, we'd use energy equals charge times the energy per charge. And if you remember, the other label for voltage is joule for coulomb. You take your charge, which you calculated in part A, and multiply it times the voltage to get energy. Conventional current, we normally talk about electrons moving, but conventional current talks about protons moving. So this is basically just information for you in case you go on in physics and you wonder, why are we talking about protons moving? We know that protons are not moving, but conventional current is devised this way so that it envisions protons moving around a circuit. We know that the electrons actually flow the opposite way, but conventional current, which is how some books will note current, actually occurs from the positive part of the battery or EMF voltage source to the negative side. Resistance is just a ratio of voltage to current, and lots of things have resistors in them. The filament of a light bulb is a resistor. So V over I, or voltage over current, is R, which is a constant. If it is, it's not always a constant, but if it is, then it is said to be ohmic, or it obeys Ohm's law. The symbol for resistor is R, and it's shown by a zigzag line. So resistors resist electrical flow. So if you see this circuit down here, the positive part of the battery showing conventional current going around this way, leaving the positive, going around the circuit, and returning to the negative side of the battery. For example, if resistance is a ratio, volts to amps, you could measure the voltage in the amps in a certain circuit and make a ratio. And you would get what's called resistance measured in ohms. Resistivity is something that we will not study specifically, but you may see it on the morning set exam. Resistivity is a constant and depends on the material, and it is a ratio of length to area to find the resistance, cross-sectional area, and the length of the material. Different materials, like I said, have different resistivities, which is the Greek symbol rho, or it looks like a cursive P, and that's the symbol standing for resistivity, which would go in your resistance formula. We will not make calculations and not be tested on that, but the idea that different things would have resistance is a concept you need to be familiar with. We'll skip that since we are not making calculations. Impedance plethysmography has to do with resistance, and checkpoint number 2, I'm asking you to look up impedance plethysmography and be ready to tell what it is used for. Interesting biomedical application. We're going to skip this as well. It has to do with temperature. Resistivity affects temperature. Alright, electric power. Power is current times voltage, and the symbol for power is watts. The equations for power, I squared R, or V squared over R, all derived from Ohm's law. If I substitute IR for V, I would have I times IR, or I squared R. And again, if I substitute for I would have V over R here, or V squared over R. So those are your three formulas for power. So if we wanted to know what the power delivered to our light bulb and our flashlight, and we wanted to know the energy value, we could look at power is I, current, times V, voltage, for 1.2 watts. Energy would be power times time, since watts is broken down like a joule per second. Joule per second times seconds would give us joules. Alternating current reverses direction. Because of the power that's generated in an alternating current generator, the current flow changes direction frequently. The equation for that is V equals V max sine of 2 pi frequency times time. So depending on how many cycles are made per second and how long the circuit has been running, you could calculate the V. So somewhere along this line you would calculate a V based on the frequency and the time that the circuit has run. The VO plus and the VO minus are your maximum voltage values. They're called peak voltages. In circuits that contain only resistance, the current reverses every time there is a generator reverse. So it is directly related to the reversal of the generator. Not always the case if there's not just resistors, and we'll get to that shortly. So to calculate the current is V over R, which would be your V max over the resistance, sine of 2 pi ft. In other words, since I is the same as V over R, the peak current would be calculated by substituting V over R into your equation. So you could also calculate the power. You could calculate the maximum power, or you could calculate the power at any time during the cycle. So the peak current and the peak voltage values would give you the power, the peak power, or you could calculate the average power, which would be half of the peak power. So halfway in the amplitude of this curve, if this is the peak at the top, then this would be the average, or halfway through. So for alternating current, you have the following formulas. V equals I times R. V, root mean square, I, root mean square, and R equals V times I equals I squared R, and P equals V squared of R. These are all the same as the equations for direct current, except that you have an average when you talk about alternating current. With alternating current, you have the regular resistance, 8 ohm speaker, and we're asking to find the RMS voltage, which is the root mean square, or average, the root mean current and the average power for this circuit. If we follow that along, the root mean square is just the maximum divided by the square root of 2. So I look at what the maximum is, and I take square root of 2 into that value. To find the root mean square current, I take the root mean square voltage, which is what I calculated before, and divide by the resistance. And to find the power, I just multiply the two root mean square velocity and currents. So the current calculated, the voltage calculated as the average will give us 72 watts. So that's not the peak power, but the average power for the circuit. This talks about extension cords heating up. That's a good safety thing. But if you have a larger, the point is if you have a larger gauge wire, you're going to have a lower resistance, which would decrease your chance of that resistance heating up because there is a temperature factor with it. We are going to address series and parallel wiring in person. But I wanted to give you an overview. Series wiring gives us gives us one path for the current. Parallel wiring gives us a branch effect. So this is series, which you're familiar with. To find the series resistance, you just add the resistors 1 and the resistors 2. We do that because the voltage drop across 1 is I times R, the voltage drop across 2 is I times R2, factor out an I, and you get R1 plus R2. So that's how we derive the equation for series resistors. For example, 2 resistors in series, 9 ohms, 12 volts. We want to calculate the current, the power, and the total power. The power in each. So, to look at that, we would say the total resistance is 9. So that makes our total current 12 volts over 9 ohms. Our power is I squared R, which each of these resistors gets the total current. So each resistor gets 1.33 amps. So I squared times its resistance, and I squared times the 3 ohm resistor gives us the values for the power for each of the resistors. Then you simply add the power for the first one plus the second one. Okay, that's series wiring, and PDAs. Another thing that's kind of obscure, but it's talking about touchscreens. So you actually make contact, and you can create a situation where you have resistances to certain points given a coordinate system. That's how they detect where your stylus might be or where your touchscreen point would be. Parallel wiring, you have branches. This is the same as this configuration. There's just a branch. There's a choice right here. There's a choice. If I send the current out here, right here, there's a choice where the current will go either I1 or I2. So both of those resistors get the same voltage. Your houses and buildings are wired in parallel. If you think about this conceptually, you can see that the cross-sectional area in the series would get all of the current. If we took these two currents, they would add to the total. 500 gallons of water, break it off, 500 through here, 500 through here would come back together as the total. So in order to calculate our resistance in parallel, we just take the inverse of each of the resistances. in parallel, you're going to find the inverse and then make sure that you take the inverse at the end. I equals V over R there as well. So that is an overview of series and parallel wiring. We will talk about combined series and parallel circuits and how to calculate the voltage, current, and power for each of those.